Welcome to Chapter 3, everybody. We're now going to be talking about numerical descriptive measures and how they apply to the data we've just pulled through Chapter 2 on the quantitative side. So in this chapter, there's a lot to cover. We're going to cover the basics. Basically, central tendencies such as the arithmetic mean or average, as you would know it, the median, the middle value, and the mode. We're also going to take a look at percentiles, and the most common is the 50th percentile, which is the median, but we'll also talk about the 25th and 75th, which give us this interesting range called the interquartile range. And then we'll talk a little bit about the box plot. It's hard for us to develop that without special software, but it does show up a lot, so it's good to know what it's doing with the interpretation of the percentiles and how we calculate them. Then we'll talk about a different kind of mean, more in the finance or economic side, the geometric average mean, mean return in this case, and the average growth rate, when we're not given returns, but we're given values that we need to convert to growth rate and from growth rate to a geometric mean. Then we're going to step away from the idea of central tendencies and move into measures of variation, such as the range, the mean absolute deviation, how far something deviates from its mean, and in terms of absolute value standing on average, the general variance, that's the sum of the squared deviations as we'll see on average, standard deviation, which is the on scale apples to apples version to your data, which is nothing more than the square root of the variance, and this interesting thing called the coefficient of variation. It gives us some kind of insight in a comparative sense to two different sets of data to see which one may be more meaningful to you. Then we'll close by talking about something called the Chebyshevs and the empirical rule and how they allow us to view data quickly in a back of the envelope sense, determine how many observations fall close to the mean, and it'll lead us to the direction of something called confidence, but it'll start with this thing called a z-score, which many of you have seen. We'll also talk about them when we have our already aggregated data, group data. Can we take something we would get in a meeting in a table or chart and convert it back to the very common things like mean, standard deviation? Then the last thing we'll do is talk about how do we look at in two space. Now we saw scatter plots in chapter 2. How do we look at XY coordinate points and see how do the X's and Y vary together? Is there a sense of covariance? Covariance is an unscaled form of this association. Correlation, which is based on covariance, is a scaled form. And what we're going to be doing in Chapter 3 is a lot of work in Excel. You're going to see a lot of videos linked here below that throughout this, that will allow us to move in and out of Excel as much as we possibly can. Let the program do a lot of the work for us, but it does help us understand by building the models in Excel. So what do we start with? Let's just take a look at an investment decision. You've got a counselor at a bank. She was asked by an experienced investor to explain the difference between the two top performing mutual funds. You've got one for precious metals and mining, we'll call that metals, and one as an income fund. So they're two different funds and they're going to have returns. And we have data over the years 2000 to 2009, so we're going to see a nice cycle. Here's the data starting in 2000, running all the way through 2009. Notice the big dip in 2008. So this is real live data that we've seen. We want to look at the typical return for the mutual funds and look at some of the risks that are associated with it. Maybe the coefficient of variation can help us out determine which one. Just because you have the best return, the variation that goes along with it might lead you to have what you thought to be a good investment not be so great. So how do you take this data that we just saw and start talking about something called a mean? Well, the mean is simply the average. So when we have a sample, which is a subset of the population, we call this X bar the sample mean. So we'll sum up all the X values that you have in your subset and divide by the total number in your sample. If you have an entire population, just sum up all the values and divide by, we call this little n, this is big N. This would give us the population mean, called mu. These are important because everything that we deviate will deviate from this mean value. We're going to do most of our work around the sample mean because these are subsets and smaller samples. Populations are great if you have them, but it oftentimes is not. It's beneficial to you and is actually exhaustive and painful to measure an entire population. So if we take a look at that metals and income fund data, if we look at both of them together, we're going to sum up all of metal, all of the income. So that's what we're doing across all their returns. Sum them up, divide by 10, and you get an average return of 24.65 for metals, and income 8.51. Let's jump over to Excel real quick. Here's that data. So here is the data you just saw. Now there is no mean call in a function in Excel. The call is something called average. So if I run the average value for each, I'm going to get 24.65 and 8.5. That looks a lot like what we just saw. Those would be the arithmetic averages, but you all know better. Ultimately, what we'd have to do is value this because these are returns. We would move to that geometric mean to more appropriately value them. But to start, here's what we have. So we looked at these introductory averages, sum them all up, divide by the total number in the sample size 10. We can also look at other central tendencies, and those central tendencies are things like the median and the mode. The mean, well, the problem with the mean is it's sensitive to outliers. What that I mean is that the mean tends to gravitate to the extremes. So if you have one particular person, in this case the owner or president of the company, when you put their value in 550,000 and create the mean, you get a return of the population, it's a very small population, 154,000. Notice that's more than everybody but the president. It doesn't really reflect what's happening at the company. Something like maybe the middle value might make more sense. Maybe $90,000 is the better salary at this company, Ace Tech. So when we go back to this precious metals, we can do that as well. Here we've created the mean, but if we wanted to create the median, the middle value, as we'll see here, and I calculate it in a bit, we could do that too. And notice the values are different than what we saw for the mean. But I'm getting ahead of myself. The mean isn't always the best. So sometimes we have to look at others, such as the median. The measure of central location, usually not affected as much by outliers as the mean value, but to calculate it, we simply take the data and arrange it in ascending order from smallest to largest. If it's an odd number, pick the value in the middle, that would be your median. Now the other one is if it's an even number, the most common way is to take the middlemost two values and take their average. You can also interpolate if you want to look at a weighted value in the middle, but by far the most common is simply to take their average. So if I take a look at, say, those salaries, here are the salaries we just saw in ascending order. What I'd like to do, since there were 7 of them, the middlemost value, 4, so there's 1, 2, 3, 4, 5, 6, 7, fourth observation is 90. That would be your median value. Including this value, looking down, there's at least 50%. Taking the same value and looking up to the largest value, including that value, there's at least 50%. If I take something that has even, say the metals fund, with that one, I would have to take the middlemost two values, take their average to find the average, in this case median value, is 33.83% in terms of return. Not too difficult to calculate, especially in Excel as we just saw. It's just a function call called median. But that's not the only one. There's also one called the mode. And the mode is the most frequently occurring value in any data set. Now the problem is many data sets have no modes. In those cases it's not useful. But in cases where we have one mode, which we call unimodal, or two modes, which is bimodal, it actually can help us look at the shape of the distribution. And we'll talk about that more. But what I said earlier was that the mean gravitates to the extreme. So as we saw before when we looked at the histograms, something that would skew to the right, if you imagine the skew to the right, all the way to the right, imagine that's the mean. It gravitates out. The one that goes in the middle would be the median, and the one that has the highest point of the entire histogram as it skews to the right would be the mode. So mode, median, mean in something skewed to the right, skewed to the left, working from left to right, all the way out into the tail, you'd have mean, median, mode. Now, in this case, the most would be 40. So we saw that the average was over 150, the median was 90, the mode was 40. That's kind of all over the place. So this is really a skewed data set and difficult for us to do a lot of interpretation, but it does give us a sense of where to start. So if I looked at that set of data, and I took the zeros off to make it easy to read, let's just take a look and see. So for the average, take a look at this. Here's average, here's median, here's mode. If you didn't have a mode, it would just come back with NA. What's interesting about all this is we can go back to the original metal set. We can use some powerful functions in Excel to help us calculate. Now, this is going to require you to go in and use the analysis tool pack. And with it, all the wonderful things that data analysis has. Now, I have some videos out on our Canvas site to show you how to do this, but just a quick refresher. I'm going to go in and use File, Options. You're going to see add-ins pop up. At the very bottom where it says Excel add-ins, click Go. All you have to do is check the analysis tool pack, click OK, and then you'll see under Data, something called Data Analysis pops up. If you're using a Mac or you're using some kind of Chromebook or web surfer, you're more than welcome to use Xavier's virtual PC and use our version of Office. Not all versions of Office outside of PC actually have this. So if you're using a Mac, most likely, unless you have the most recent version, you do not have this option. You'll have to use the virtual PC. But with the data analysis tool, you can create these wonderful charts to give you all this information. So with data analysis, there's something called the descriptive statistics tool. If I click on that, and in the input range, all I'm going to do is highlight what's in the metals. I can highlight with the metal label, clicking on labels in first row, put the output just right below this, and click on summary statistics so it gives me everything. I highlight my data, have my metal label in the first row, I have a place to put it, summary statistics. And what it does is it gives me all those things that I want. Mean, median, there's no mode in this data. We also know what the min, the max, the count would be. And those are the things we've seen. Now we're going to spend some time looking at standard deviation and variance, but the other things will eventually hit everything on this entire list. This is an easy way to get all the data. Now it's not iterative. If I make a change over here from 7.34 to say 9.34, I have to rerun it, but this does save me a lot of time. Just a heads up. Now, we saw how to calculate this, and we just talked about this descriptive statistics tool. Both wonderful things and should give you to the same degree of accuracy in Excel. The next thing we would cover is weighted means. Now you've seen this before. Weighted means are nothing more than what you would see in calculating your GPA based on the number of credit hours. So what we're going to calculate is a weighted mean, where we take the weight of a particular value times the observation itself and create the mean based on that. For example, let's say we have 3 exams, exam 1, 2, and 3. 3 scores. You got a 60 on the first, 70 on the second, 80 on the third. And the weight on each is the first is worth 25%, the second is worth 25, the third's worth 50. If I multiply the 25% times 60, 20, 70, 50 on 80, assuming that each test is worth at max 100 points, your weighted mean for those scores would be 72.5. Reality is for this class, you're going to have to do the same thing because our Learn Smarts, our homeworks, and our quizzes all have different weights across a spectrum of number. In this case, we'd have 8 different modules. Or in some cases, we'd have even more. So if I just took the average 60, 70, and 80, my average would be 70. That's the arithmetic means. But the reality is, because you did so much better on the third exam, you should get credit for it with a fuller value in terms of its weighting. So you did a little better because of the weighting on the last test. If I want to see that done in Excel, start with my scores, create my weights, make sure you clear the table and guarantee yourself that you're actually summing to 100. Here's the 100%. Sure it's the case, that sums up. I will multiply. Everything starts with an equal sign. That engages the function F2 times G2, and I'll copy that down and sum that up. Here's the average of the scores, sorry. Here's the average of the scores. And again, the weighted mean outperforms. So it isn't very difficult to create, and you can actually think about how you've done this in the past with your GPA or QCI or QPI. There's so many different things we calculate for colleges now as we move in and out of schools. The next thing that we're going to cover is something called percentiles. Now the median was the middle value, so it's the 50th percentile. But that's not always the case. Sometimes we want the 25th, the 35th, the 75th. If we're talking about the 25th percentile, that's the number we're looking down on. So if I'm in the 25th percentile, I'm looking down on, including myself, the lowest 25% of all observations. If I look the other way towards the highest, I'm looking up to the highest 75%. So it's 100% minus the percentile that I'm located in. So much like we did with the calculation before, we arrange the data from low to high. We decide what percentile we want to look at, but we have to find it positionally. First step is finding where are you on that ladder of ranking. Then we'll figure out where you are based on a weighting mechanism, based on a simple score from this L sub P. So we know the number of the observations that we have, say N. We guarantee that we're in the spectrum of one more than that, so we're looking beyond that space to whatever percentile we want. Here's what we do. If we have a range of values here, and this is from that case where we looked at the metals, for example, want the 25th percentile. So where we stand looking down, we get the lowest 25%. Where is that? Well, there are 10 observations, so you take 10 plus 1, 25th, and you get 2.75. That's going to put me in this space, the 2.75 position. 75th puts me in the 8.25 up here. Now, we know the value for the 25th percentile is between negative 7.34 and 8.09. Same thing up here between 43.79 and 59.45. Question is, what are those numbers? Well, this is the key, what comes after the decimal. So we know that we're 75% of the way from 2 to 3, but we're only 25% of the way from 8 to 9. 25 from 8 to 9, 75 from 2 to 3. And what we'll do is take that value, so we know that we were between negative 734 and 809, the lower end 734, which is negative, remember the 75 we had here, multiply it between the difference between what you saw on the low end and the high end. That would have been the upper value, that would be the lower value, and you get 4.23. That is the 25th percentile. Same thing for the 75th. You take the 25 that comes after the 8 and multiply by the difference and add to the lower value rung. So this is your 25th, this is your 75th. The difference between them would be the middlemost 50% of all observations. We call that the interquartile range. Very important deal because it allows us to get a better sense of where the center of your data is, especially if we have these goofy things called outliers floating around. Just said it, an outlier is something that falls outside of what we would normally expect. And we'll spend a lot more time talking about how do you actually identify what an outlier is. But when you look at these specific charts called box plots, you can get a sense when people display them to you what an outlier means. So we want to graphically depict this box plot or box and whiskers that has our low end, our upper end, our 25th, our 50th, and our median is interlined. So this between the edge of the box is the interquartile range. Small, largest, in Q1, Q2 interquartile. Really simple. So from the metals, this was our low, this was our high, Here is what we have in the space between Q1 and Q3, and we knew the median was 83, 33, 83. So let's just take a quick look in Excel. I did these calculations as they would be, and I'm going to make sure this is available for you for our classwork. With the 25th percentile is calculated, the 75th percentile is calculated, the values we just saw with the reflection of the 75th, 2.75, and here the 25 based on this. So we also know what the median is, the median value, just to give us a sense. I calculated that as well. And I'm going to find out what the median value is just the same way. Notice when I calculate it using the formula here, it gives me the same answer as the median. So as I look at this and establish what we just saw, my question would be, are there anything that outlie what's happening within our range? So is something not making sense? So smallest, quarter, third, and largest, can I find this out? The interquartile range runs a spectrum of 43.48 units. Notice the full spectrum range from negative 56 to 76 is over 132. That's quite a bit more. So the outer 50% going all the way up gives us 132, more than 132. Well, that's almost 90 more than this one. So there's a lot more stuff out here, especially on this side. Can we calculate whether or not something doesn't belong? Well, if we know the interquartile range, let's just say that if you are 1.5 times the interquartile range either way, outlie. So 1.5 times 43. So if you're beyond 65.22 each way, then you're out. So if I take the first quartile, subtract what our value would be in the low end, if that difference is more than 65.22, you're an outlier. Upper minus this, if you're more, you're an outlier. There's no outliers in this data set, but let's take a look. Here's the interquartile range. I'll blow this up a little bit for you so you can see it. Here's the interquartile range. Here's 1.5 times that value. So if Q1, which was for a value for us, the first one, a value here, Q1 minus what the smallest value would be, 56 negative, gives me 60.25. That's not an outlier. And if I take 76.46 and subtract it from what we find for a value of Q3, 28.76, that's also smaller than the 1.5 times IQR. Since neither one is bigger than this, it's no outliers. I'll leave this up here just for a second so you can see how they would have done it. But mine, as the sheet that I have, looks very much the same without all the language. You can see the references that they make. You can pause it here if you need to. On. The next is the geometric mean. I know we're covering a lot of different things, but the geometric mean is very important because it gets us away from what would normally be the just general arithmetic average, arithmetic mean. This allows us to look at growth rates and investment returns. For example, and all of you know this, but if I have 2 years of return, 2009 I got a 10% return, 2010 I got a negative 10% return, just a simple straight mean, 10 plus negative 10 divided by 2, that means that if I had $1,000 at the start of 2009, I'd have $1,000 at the end of 2010. Well, that's truly not true, because through compounding, the magic of compound interest, I'd start off with $1,000, and at the end of the first year, I'd have $1,100. But that $1,100 is now taking the force of losing 10% of its value, or $110. So at the end of 2010, I wouldn't have $1,000. I'd have only $990. So we know that we're less than $1,000, so there is a negative return. That's a geometric piece. I'd like to see 990, where I ended, from where I started, over a 2-year interval. So I take the square root of their difference and subtract 1, and I get this 0.5% return, which is negative. What we're doing is creating a geometric mean return over a period of time. So if I look at the metals, for example, and the income, they can be converted, each of them, to a return. Take 1 minus or 1 plus, it's 1 plus each. In this case, it reduces. This was a loss in the first period all the way through the end. Take the 10th root, and you find out the average return for each. Let's take a look at that in Excel. Here's what we did initially for 1 to the straight average. But when I take a look at them at the end of the year, end of year 1, so I take 1,000 and compound it, end of year 2 and compound it, 990. So I would take 990 divided by 1,000 and take the square root. So I'm raising to the power of 1 over 2. Another way to do it is simply to take a look at the compound for each. So that's a 10% return, 1 plus that. 1 plus negative 1 is 0.9. And if I just simply take the square root of their product, I would get the same thing. Mathematically, it has to be the same. Go to a bigger problem. Here's metals, here's income, and we saw these from the very beginning. There's metals and income. Now, I'm going to convert them from their seen as percentages to their decimal. So 7.43 negative becomes negative 0.07. What I'm going to do then is I'm going to add each of them to 1 so that I get their yearly return. Then what I'll do is simply say, let's take the product, and let me blow this up for you a bit so you can see it. I'm going to take the product of all those individual returns, and there's 10 of them, and I'm going to raise it to the 1 over 10 power and subtract away 1 so that I can get it down to its compounded geometric return of 17.79. And I'm doing the same thing with income. So I'm able to create something that's a little bit different, 17.79, versus if I just took the straight averages of each, 24 and 8.5. The true geometric returns are the ones we want. These are the ones that are the true returns that we're looking for. This is what we want for geometric in cases where we have compounded values. We can also look at geometric returns, geometric means with average growth rates when we're given values that aren't actually given as a ratioed value between 0 and 1 to make it represent itself as almost like a probability. What happens when we have something where we're given, say, sales in a particular year? Say these are just units of anything. They could be refrigerators. Doesn't matter. In each of these years, and these are sales. Blow this up a little bit. First thing I'm going to do is take a look at the growth rate. How much between 2005 and 2006 did we grow? We went from 6,600 to 6,636 to 10084. So I take 1084 minus the 6636 and divide by the base, 6636. So we went up by 51% based off of this. That's our growth rate. General growth rate, I should say. It's not we went up by, it's a general growth rate. And I'll move that down, but I can only go to 4 places because there's nothing beyond. So we only have 4 to view. If I convert them as if they were as if they were interest rates, or we're trying to compound something, add 1 to each, I could do that and calculate and say, let's take the product of that grouping. Product is a simple call that we would see in Excel for multiplication of a group. Raise it to the 1 over 4th power, subtract 1 to get us back to what the rate would look like, and we get an 11.84% rate of growth. I could also use something called geomean, which is an interesting call in function Excel, the geometric mean over a period. Any way you want to do it is okay with me. Just make sure you're comfortable manipulating the functions in Excel. Explore them. If you're very comfortable with this, use GeoMean. I think it's a wonderful tool. It works just as well for any of these. I could have come over here and used GeoMean here as well. Sorry. And arrived at a very similar solution. In this case, a very exact solution. Should look exactly the same when I'm done. Just saw this over a period of time. We can calculate this quite easily. And here's how they would have done it in Excel, very much like I did. At the bottom here, they're using another function in Excel called the rate function that allows you to do something another way. So you're seeing 3 different ways to do it. Each is acceptable, each is perfectly fine, and you will arrive at the same solution every time. So we're done with central tendencies. Central tendencies drive the train because you can't measure variability without them. But the variability that we have to discover will be multifaceted. We'll look at things like range, the difference between low and high, the mean absolute deviation, how far an observation deviates from its mean. Take the absolute value and find the collective for that. Then we'll look at the standard values, the most common, the variance and the standard deviation. Then we'll use this thing called the coefficient of variation, just to give us a sense when we look at 2 data sets, which one might we choose beyond what our senses would tell us. So range, simplest, it's the easiest to calculate, obviously, most sensitive to extreme values, much like the mean. So when we have something like the metals fund and the income fund, as we saw before, go over here, the metals fund, income fund, we know that the largest and smallest values here, if I took the maximum value of metals minus the minimum value of metals, I'd get 132.48 as the difference, and the same thing for income. So it is a huge swing, and it tells us really nothing other than the width of all the data. But it does give us a simple start to see whether or not something is just wildly different. The mean absolute deviation is very interesting because what it's trying to do is come up with an average on a positive note without identifying but in the negative direction. So it will tell us the absolute difference of each observation from the mean. For either a sample, there's X bar, notice the small n, that's for the subset size, U for the population, this is the parameter, this is the statistic, sample size, population size. And what we'll do is we'll find out what the mean value is. We'll then deviate the mean from each observation, take their absolute value, and sum them up. For us, we know the mean of metals. We've calculated that before. We're using the descriptive statistics tool. The mean. So the mean absolute deviation is going to take, so I'm going to use a call called ABS. That's the absolute values function in Excel. And I'm going to take the ABS, between metals and metals mean. Notice I'm using a reference here, an absolute reference. I'm locking in the cell, so the $ again locks in the column J, and the $ locks in row 4, so J4 is here. And I'm going to carry that all the way down. Then what I'll do is I'll sum it up and divide by the total number n, in this case 10. I'm counting them up, but I already know it's 10 because it's telling me over here. I'll do the same thing here with the same absolute reference. So what I've calculated now is the mean absolute deviation for metals and income. Now, there's not a lot you can do with the mean absolute deviation. It's just one more trick to have if someone asks how far is this thing deviating. But what we would use it for, something like this, is just to give us a sense of how far it's moving in a direction away from the mean, regardless if it is low or high, above or below the mean. We're just seeing how far is it deviating. You want that number to be quite small on average. Now, the one that's most important is the variance. Variance, if we start with the population, we call this sigma squared. It says how far does each observation x of 1 deviate difference from the mean squared on average. So it is the sum here of the squared deviations on average. That's the variance. Standard deviation is nothing more than taking the square root of it. For the sample, it's the sum of the square deviation from the mean on average, but we're reducing by 1 here. And what that does is it gives us a wider spectrum. So if you imagine, if you take something and divide by 10, you get a ratio. If you divide by 9, the little bits that you would divide by, say you divided by 90 by 10, you get a value of 9. But if you divided 90 by 9, you would get a value of 10. So this variance, we do this so that we get a broader, typically larger value for variance, because we're going to deviate more because of the sample size and the fact that you're drawing a subset. This is also referred to as degrees of freedom, and we'll get into more examples of degrees of freedom later. Don't worry about it now, just know that it's subtracting 1. Square root also gives us S, which is the sample standard deviation. And they're easily calculated as well. Now, the one thing is, they can be kind of brutal to calculate. That's what's wonderful about this, is that I can calculate the standard deviation in each of these. But if we want to take a step back here, I could also, if I so choose, calculate these values directly. So for metals, for example, the variance, I would do something called var. I'm using equals var dot s. That's the variance of the sample for a range. The standard deviation is the square root of that. I could also use something called stdev dot s, the standard deviation of a sample in that particular range. Now also notice there is something called var dot p and stdev dot p. Those are when you know the population. Instead of dividing by n minus 1, you divide by n. Get it? So, those values give us the baseline. Variance is a squared term. So if this were, say, apples, and you're looking at the mean number of apples, this would be apples squared. The square root of it brings it back down to like terms, so you can compare S to X or X bar. The coefficient of variation is an interesting thing. It allows us to compare normally multiple sets of data and see how they are dispersed by their standard deviation in comparison to the mean. We would do this, we have several data sets, and we do it because the lower the CV when we ratio our standard deviation to mean, the lower the coefficient of variation, the smaller the errors are going to be when we ultimately predict. So let me just take a step back here. I didn't mean to get ahead. So let's just take an example. Stock A, one great stock, has an expected return of 15%. Stock B returns 10%. So you're thinking stock A is a better bet because it's 15%. However, if we just relied upon means, we get ourselves in trouble because we don't know how much variation is happening with 15. 15 could be you have a negative 100% return once, positive 100% return one time, and a 45% return another, and that is on average would be 15 on an arithmetic sense. Of course, you have to geometrically do it, but I'm just giving a rough estimate. Let's just say A has a standard deviation of 10% and B has 15. So the ratio of A would be 15 as your expected return with a 10% deviation, or coefficient of variation of 0.67. The coefficient of variation for B, 10%, it should actually be 10% divided by 5%. We're looking at something quite a bit less. So the coefficient of variation that we have would be a little bit less. If you got to think of the ratio as being reversed, the coefficient for B is actually a better investment because the variability, which is less, makes it a better bet. So in the case of metals versus income, even though it has a lower return, has less variation. It seems like a better deal. All this can be done in Excel, and I did this here as well with a coefficient of variation. Here's the coefficient of variation. I'm taking a look at the standard deviation, and I'm dividing the standard deviation by the mean, and it's pretty simple to calculate. Very straightforward. Make sure you're using Excel as much as possible. Take your time to learn var.s, var.p. You can even do something called avdev, gives you mean absolute deviation. It saves you a lot of work. Last couple things we want to cover. Distribution. So we're going to start looking at how data distributes itself around a central point, usually the mean. So with that, we want to make sure that we have some rules to play with, such as Chebyshev's rule. Chebyshev's rule is an interesting rule that allows us to look at how data would deviate about a mean in cases where we want to see from a central standing point how many observations would fall. So, for example, with Chebyshev, we like to know from a center point how many observations fall within, say, 50% of the center, 75% of the center, and so on. Chebyshev's is not relying upon you knowing what the distribution of the data is. Chebyshev's, because of that, is simply formulaic. We use 1 minus 1 over k squared. Anytime you impute value for k, such as 2, put in 2 here, and we would say 75%. So within 75%, at least 75% of all observations fall within a particular range. In this case, within 2 deviations, at least 75% of all observations fall within that particular set. The empirical rule, and this is the one we're going to use, is based around something having a mound shape or normal distribution. In this case, it's straightforward. We know that within 1 deviation either way of the mean, so take the mean and add and subtract the standard deviation, about 68% of all observations fall. Within 2, about 95, and within 3, just about everybody. So this one's straightforward, but you have to know that it's normally distributed, and you have to know that it's mound shaped. In cases like this, it's very straightforward to helpful for us because it gives us a quick sense of how many fall, but as we'll see going forward, using the normal distribution is a quick check to see whether or not it makes sense. The advantage of Chebyshev's is more than anything else, you don't have to know distribution. The empirical, though, is very exacting. And just to revisit Chebyshev's real quick, this is important. And if you look at this example here, you got 280 students, you know what the mean is, the standard deviation. So you're adding and subtracting 8 from 74, much like you did here. So if I add 8, I go up to 82. Add 8 more, I go up to 90. That's how we got between 58 and 90. If you made it 3 here, do 3 squared, and you can see how we would reduce this. So this one is based around the number of deviations. The thing about it is, once you get beyond 3, empirically, it's very difficult to find any observations. But 3, for Chebyshev's, you're still going to find some because those distributions aren't so easily recognized, such as the normal distribution. One of the other things we'll deal with is this thing called the z-score, and many of you have already seen z-score. It's a standardizing score. We often say, I'm going to normalize data. Well, the z-score is a big part of that. What a z-score does, it says, take an observation, subtract its mean, divide by the standard deviation, and it gives you a score. Score of 0 is an absolute center, and what this does, it tells you how many deviations away you are from the mean based around the sample, in this case, the sample standard deviation. So if you had a z-score of, say, 2, that means you are 2 z units away positively to the right. I'll go back here and show you. You would move in this direction 2 units, or 2 hot points. And it's a standardization. It puts things on scale. So that when we talk about this having a standard normal distribution, ultimately we'll fall back on this. It allows us to determine whether or not something is small or large relative to the mean. And it will lead to this thing called an outlier. We move outside of 3 of these standard deviations. Again, here's 1, 2, 3. If you're outside of 3 deviations, we are saying just about everybody's there. If you're outside of 3 deviations, you're an outlier. Well, those 3 deviations can be calculated as a z of -3 or +3. Now let's talk about grouping data. Grouping data is rather complicated, but it is something you've seen before, and it helps us when we're given data in presentation. We can calculate means, deviations, and so on very easily from summarized data. Just like we calculated and created it in Chapter 2, now we can take it and create values from it. For example, we were able to create a table just like this in Chapter 2, where we ran up values between 300 and 400, 4 up to 5, 5 up to 6, in terms of the housing prices in a particular market. Now, we used a method to get there. We know it's elegant when it's between 5 and 20, and the class sizes are usually pretty elegant in terms of values between 5, 10, in this case 100. We know the frequency. What we're going to do then is find the midpoint. So if you're just given this table saying, this is what we have, here's the frequency, what I'm saying is just given these two sets, these two columns, I'm going to be able to calculate the mean, standard deviation, and variance. And I do it pretty simply by saying, let's find the midpoint halfway between 3 and 4. So add 300 and 400 and you get, and divide by 2, you get 350, and you can see how easy that is. Multiply the frequency times the midpoint. That value becomes summed to 18,800. We'll create a mean value from this. So let's take a look at that. Here's where we just were. I'll blow this up so we can take a quick look at it. 18,800. The mean then takes the 18,800 and divides by the total frequency. So the mean value for this data set based on this midpoint approximation is 522.222. What I'm going to then do is take how far is the midpoint from the mean. I'm going to square it. This is how we do variation. Remember, variation is the sum of the squared deviations on average. So I'm going to square them, but I'm going to multiply by the frequency, and then I'm going to back that right out at the end. So I'll do that for each one of these. Notice the absolute reference to this, but I'm going to let the others float. What I'll do for the variance then is sum them up and divide by n minus 1. So remember, it's the sum of the squared deviations on average, in this case, since it's a sample, n minus 1, in this case 36 minus 1, which is 35, we get a variance of 10,634. The standard deviation is nothing more than the square root of that. From this, we could go ahead and start creating, if we needed to, we can create z-scores. We can start talking about how many deviations away from the mean. So if you're ever in a situation where you're given data and you need to figure out what the mean is, and people are trying to describe something, and you want to find out what a simple central tendency is, it's not complicated, especially if you have Excel. So we're able to find out what these values are. Again, here's how they did it. You saw how I did it. I'll leave this up for a second so you can take a look and see how they would have calculated it. You can pause at any point that you need to do so. Last, and I know this is pretty exhaustive, but there's a lot to cover in Chapter 3 for us. Covariance and correlation. It's an association. We call it a linear relationship between two variables. We saw this in scatter plotting in Chapter 2. Covariance is an unscaled form of linear relationship or linear association between x's and y's. Correlation takes the covariance and puts it on scale between -1 and +1. We're very familiar with somebody saying those two things are correlated. Well, that's a directional movement. So you can see covariance, we're seeing both a sample and a population covariance. It's how are x and y varying from their means on average. So again, -1 because it's the sample, know we're giving ourselves some wiggle room here because we make sure that we're not as exacting as the population. But again, deviating from their means on average. The correlation, R or rho, takes the covariance and divides by the individual standard deviations. What you end up with are these simple measures. If we looked at things in a scatter diagram, it can get a sense of as x increases, y increases. As x increases, y seems to decrease. Or as x increases, nothing happens with y. Those things, correlation, as you can see, -1 to +1, -1 to +1 for the population are what we're comfortable with. We know that the closer you get to +1, the more one-to-one relationship we have, and same with -1. Covariance, there's no such rule. Those numbers can get astronomically high. So if you had a covariance of 10 or a covariance of 10 million, it may not mean anything differently. It's correlation that puts it onto a unit that we can compare. So if we took that metals and income and we plotted metals versus income on an XY coordinate system, it appears that as the metals goes up, income goes up in terms of their fund. So if we drew a line here, we know that they'd have a positive run, positive relationship, or a positive correlation and a positive covariance. And the calculations can be extremely intensive for this in Excel, especially if you start doing it with nesting. But if you do it using the simple functions of correlation and covariance, and I've plotted this just simple XY coordinate to give you a sense, and I even imposed a line here to see what it looked like. So it is, as x increases, y seems to increase. I'm going to use two things. First, the covariance. Since it's a sample, we use covariance.s. As most things today exist in Excel, I could have used covariance.p and found the first array and the second array. The only difference being the denominator would be greater in the this would be the population if it were, and this would be the sample population. The correlation is just simply correl. It assumes it to be a sample. So correl is the only call we have. You can use your IntelliSense, you can start typing it in, the only one we have. To convert it to population is a little tricky, but we're going to stick with the sample correlation at this point. Again, the population covariance is smaller than the population sample covariance. 350, 316. Notice how much bigger they are than the correlation. Correlation is the one that's important because that's the number that's on scale. It takes the weight of elephants to the weight of feathers and puts them on scale, and now you can correlate those two things. So that's what we're doing in this chapter. A lot of work, a lot of intensive Excel work. Should give you some really great insight in how to use Excel, especially the descriptive statistics tools I'm showing here, and some interesting functions. As we move forward, we're not going to do a lot with Chapter 4 other than a quick introduction of what probability is. Then we will move on to both discrete and continuous distributions in Chapters 5 and 6. Talk to you soon.